official Unit 1. We are going to be solving equations all the time. Review chapter was basically just working with expressions, and now we're going to be solving equations. So that begs the question, what is the difference between an expression and an equation? Well, an expression has no equal sign. You could think of that as like x squared plus 5x plus 7. Okay, this would be an example of an expression. We can do lots of things with expressions. We can evaluate them by plugging in numbers. We can simplify them, but we cannot solve them. An equation has an equal sign. And, it could look very similar, x squared plus 5x plus 7, but now we say this is equal to something like 0. And now I've got a whole different set of things that I can do. Primarily, if I have an equation, I can solve an equation, which means you will have a solution. Now, in today's lesson specifically, we're looking at linear equations. We've got all sorts of different types in this chapter, but today we're looking at linear equations. And so the degree of a linear equation is 1. And so remember, the degree is the largest exponent, and so, a lot of times, something like 3x plus 5 equals 7 would be considered a linear equation because my largest exponent is 1. But if we had something like 3x plus the square root of x plus 5 equals 7. Is this still a linear equation? Well, technically the answer is yes. This is to the 1/2 power, and so 1 is the largest exponent, so we would consider this still a linear equation. If we were to graph a linear equation, of course, we would get a straight line instead of a parabola or something like that. And then additionally, our solutions. When we have linear equations, we have 3 different types of solutions. You can get just a standard answer, like x equals 4. This will be the vast majority of your answers. And this is called a conditional linear equation. And so it just means there's a correct answer and there are lots of incorrect answers. Another thing that you'll run across is you might do all of your algebra correctly and you wind up with something like -3 equals 5. This, of course, is not true, and this is what we call a contradiction. And with a contradiction, there are no solutions. There are no values that I could plug back into my original equation that would make it true. The final case here is you'll go through all of your work and you'll get something like 5 equals 5. Now, this is a true statement, but it is still pretty weird. We don't get our answer. What's happening here is this is called an identity. And this means that all real numbers are solutions. Any number I could plug in to my equation and it would make it true. And so remember, a solution are the values or value that make the equation true. Okay? So that's always a great way to check your work is by taking your solution, plugging it back into your equation. If it makes it true, then it's a solution. If it makes it false, like this down here, then of course it is not your solution. So we've got a number of different examples here. We're going to be tying in lots of what we did with expressions. So here we go. First one, I'm going to start by using the distributive property. So I've got 6x minus 12 when I do that. And then over here, remember we've got to distribute this negative sign. So that's negative x minus 5. I've got variables on both sides of my equation. I also have some like terms that might be nice to combine here. So I'm going to say 6x minus 12 is equal to, well, 7 minus 5 is 2 minus x. I think at this point, I'll probably put all the variables on one side. I'm going to add x to both sides. Now I've got 7x. I could also add 12 to both sides. So 7x equals 14. Divide both sides by 7, and x is going to give us 2. This is, again, what we call a conditional solution, or a conditional linear inequality. All right, over here we've got some ratios. We've got some fractions. And so the first thing I want you to think of when you see all these, unless you love working with fractions, is to multiply through everything by the least common denominator. And in this case, that would be 12. So when I do this, it doesn't directly affect the denominator right away. I'm going to have 12, because remember, this is like 12 over 1. When I'm multiplying fractions, I multiply the numerators and the denominators, and 1 times all these denominators is just the same. So I have 12 times 2x plus 4 over 3. And then, well, 1 times 12 is 12, so 12 over 2x. And then 12 over 4x, and then minus 12 times 7 over 3. Well, here's the beauty of this. As long as it's truly the least common multiple, all of these will start canceling out. 12 divided by 3 is 4. Actually, maybe I'll change colors here. Okay, 6 divided by, or 12 divided by 2 is 6. 12 divided by 4 is 3. And 12 divided by 3 is 4. And so, what's going to wind up happening here is, well, I just have 4 times 2x plus 4, and that's 8x plus 16. Over here, these cancel out, I just have 6x. Over here, I have 3x. And then over here, I just have 4 times 7, so minus 28. And all of those nasty fractions went away, and I have something much more manageable to work with. 8 plus 6x is going to be 14x plus 16 equals 3x minus 28. I'm going to subtract the 3x from both sides and get 11x. Subtract the 16 from both sides. This was the equal sign. Subtract the 16 from both sides. Now I've got negative 44, which comes out to a nice cool x equals negative 4. Again, another conditional solution. All right. Moving on to our next set. So here they all kind of look the same at first glance, but if I start going through my my steps here, I've got negative 2x minus 8 plus 3x equals x minus 8. I'm going to combine some like terms over here. Negative 2x plus 3x, oh, that's x. I have x minus 8 equals x minus 8. Something weird's going on. If I subtract x from both sides, add 8 to both sides, I wind up getting 0 equals 0. This means that all real numbers are solutions. In other words, this is an identity. Right? So that's all I'm going to put right here. Right? This means that any number that I plug in for x is going to make that true. All right, the second one, again, I start doing my steps here. I got 9x minus 3 equals 9x plus 7. I guess when I subtract 9x from both sides, I wind up with negative 3 equals 7. That's not true. This means that there are no real number solutions, which indicates that this is a contradiction. All right. The final learning target for today was be able to solve for variables in terms of other variables. So here I've got a minus p equals prt. I might recognize that from some business stuff, but if I'm solving for p, um, what I'm going to do, oops, what I'm going to do is I'm going to, well, first I'm going to add p to both sides. And I'll wind up with a equals p plus prt. And here's kind of a neat step. I'm going to factor out a p from each one of these terms. So that'll leave me with p times 1 plus rt. And, well, at this point, again, my mission is to solve for p, to get p by itself. And so I can just take this whole thing, divide by 1 plus rt. Of course, I would have to do that on the other side, too. And I wind up with p equals a divided by 1 plus rt. All right. This one, I guess it's got more stuff to it. There's more numbers in it, but we're still solving for x. But you can see that with the a, with the b, it's not going to be a clean number. It's going to be another expression on the other side. So I'm just going to start going through my steps, and where I can combine like terms, I will. I'm going to have 6x minus 15a plus 4b. Over here, I've got 4x minus 2. Let's see. I want to get all of my x's together, so I'm going to subtract 4x from both sides. That'll give me 2x, but I do want to get x by itself, so I'm going to take these two terms and push them onto the other side. Add 15a, subtract 4b. That means that I'd wind up with positive 15a and negative 4b, along with my minus 2 from right here. And now I'm almost done. I've almost got x by itself. I just need to divide both sides by 2, and I wind up with x equaling 15a minus 4b minus 2 divided by 2. Do I have any like terms that I can combine? Nope, nope, nope. And so this is my final answer. All right, well, that takes care of